here we go. So this is what, lecture number 44. Wow. And today is the 29th of 30 days of April. So what we've been talking about are these line integrals. So and as I said, it turns out these line integrals have many applications. They also have a few different ways that we can write them. So this is one line integral. Remember, we also said sometimes people adopt this shorthand like this. And then we also suggested that there's even another way, and we sort of went through this calculation before, that you can also think of this as the integral over some curve of this form, where you now notice I'm writing a lowercase f now. It's not to be confused with capital F. And sometimes we write it like this. And remember, we talked about what f and g are. Little f and little g are the quote-unquote components of f. In dx and dy are these things called, the differentials. So I think Austin, it was you who mentioned, are those like two integrals, and we did an example of that form. And I said you have to, it's sort of like, I think you used the correct term, like an abusive notation, I think was the way you stated it. I think it was you. Anyhow, these are three ways to write the same thing. So this is a math class, and technically in a math class, we don't need to tell you these things are important. We could just say we study them for the sake of studying them. But these integrals, I've given you a few actual physical applications of these, from work to flux to this thing called circulation. And there's actually plenty more applications of these types of integrals. And it turns out there's a beautiful connection with these types of integrals when we integrate around the closed curve. So I alluded to this at the end of class on Monday. So if C is closed, and it doesn't necessarily have to be simple, but let's just kill all those technicalities with this. So suppose our curve is nice enough. What can that mean? That means things like it's simple, or has certain things about its continuity and then what's happening inside of it. These are all technicalities we're not really worried about in Calculus 3. What we can do is we can relate this. Remember, if it's a closed curve, we put this little circle around the integral so the reader knows it's closed. We can relate this creature to this. So where D is the region enclosed by the curve. So if we draw a picture of that, Oh, by the way, let me go back to the first page. It should be noted in this particular section today, we're only talking about R2. So let me be very clear here. So today, F is a vector field in R2, the plane. So it's not, we're not worrying about 3 dimensions today. That will have its day coming up, but that's, right now we're only worried about curves in the plane. So if I draw a picture, suppose I have some curve and maybe we talk about it, this curve has this orientation that I've mentioned, this direction. So how do we interpret this? These arrows suggest, what these arrows suggest, imagine an object is moving along that curve and it's going in the direction of those arrows, which if you learned middle school math, we call that counterclockwise. And then if this is C, what is D? Well, the region inside is D. Does that make sense? So it turns out that in some physical phenomenon, and you can imagine this, you can, and we'll even mention a cool, interesting applications. It turns out that if you have something, imagine a particle moving around the boundary of some region, that the physical properties of how that particle moves is somehow related to the size you're going to see, or not necessarily just the size, but some inherent properties of what's inside. Does anybody have a question about this setup here? Okay. So this relationship has a name. It's called Green's theorem. So let's state it. And as I've said to you guys many times in the past, if a theorem has a name in front of it, like the mean value theorem or the fundamental theorem, or if it's got somebody's name attached to it, Taylor's theorem, now we have Green's theorem. That means these things are important and they're used extensively and they have many applications. You don't see any textbooks that have O'Grady's theorem in it, do you? No, right? Not right now, at least. But we do have this thing called Green's theorem. Now, again, do we want to say the specifics? I guess we should, at least for the sake of the very first time. We'll say the following. So suppose C is a piecewise smooth curve. This is, again, a bunch of technical jargon. So this is technical jargon. I'm never going to give you a problem where any of this stuff matters in Calc 3, but these are the hypotheses of the theorem. So for some vector field, which will denote having two components, f and g. So for f and g, where now we need some partials. And they must be continuous. So this is all that specifics of the nice enough stuff. I mean, you guys have seen functions whose derivatives don't exist or they're not continuous. Those are rare exceptions, but they do exist. Now, we're not going to care about them in this class, right? We're going to care about the nice guys. So for a vector field that behaves like this, what do we have? We have a beautiful theorem. We have that the line integral of f dot t ds can be rewritten as d over the following. It's the partial of g with respect to x minus the partial of y, excuse me, the partial of f with respect to y, dA. So before we do anything, let's think about what this can mean for us. The left-hand side of this equation is a line integral. The right-hand side is a double integral. And what this is telling us is that we have two useful options, if not more. Because what this theorem says, this relationship says, perhaps we have a very complicated line integral. And it can be complicated for many reasons. Maybe the vector field's ugly. Maybe the curve has a very ugly parametrization. That line integral could be a complete pain in the you-know-what, but all of a sudden that double integral on the other side can be very simple. Or the opposite can be true. You may have a very complicated double integral that you need to integrate for whatever reason. Who knows? Maybe you just like to do integrals because you're a nerd. Lots of people like to do that. Maybe you love doing double integrals and you got one that you just can't figure out. But it turns out that that double integral you might have a hard time calculating could be written as a simple line integral. So what Green's theorem does is it gives us this relationship, and one of its many uses is that it can take a hard integral and write it as an easy one. And we can often do that from left to right or right to left. Does that make any sense? Now, this is a simple, beautiful equation, and you're going to say, oh, hell no, it ain't, because you guys are still, you know, what's the old saying, wet behind the ears. Can I say that? Is that bad? I don't know. But, you know, you guys will look at this g with the subscript x, and it takes you a while to remember that, oh, partial derivative, that's right. And then you look at this f with the arrow, and you say, what does that mean? And then you're like, what's f and g again? And then you have to remember f and g, little f and little g are both functions of x and y. And then you have to remember that c is given by some parametrized curve that has an x and a t and a y and a t. And there's so much hidden behind this simple, beautiful formula. So does anybody have a question about it? All right, so this is a very powerful and useful theorem. And so I think what we might want to do is we might want to see why it's true. You know, I often don't do proofs in this class. We do a few here and there, and we often kind of just sketch things. But I think it's a good learning experience for you to see how this thing is true, even in the simplest cases. And then we're going to do some examples, and then we'll see you on Friday, hopefully. Although maybe not, because the golf courses are open again, and maybe we'll just cancel class on Friday so I can go golf. Actually, it's supposed to rain Friday, so we'll have calculus fun. Okay, does anybody have a question?
Can we do golfing calculus?
Well, we could, but that's very difficult. I mean, what, you want to know like the physics and math, the calculus behind a golf ball? Can you
Sure.
imagine how much is, yeah, go look those equations up. You can easily find them. They're not easy. Uh, you know, think about it. That's actually a good interjection because the physics behind golf ball flight and, you know, how you won, it's not much different than a soccer ball in the essence of, it's not always necessarily how hard you kick it or how hard you swing, but it's actually your technique and where the ball's hit and at what angle, you know, because what makes a golf ball fly is the spin on it, right? It's how you create spin. Yeah, and you're right. You can do physics of that. You can do the math, and it's all vector analysis. Fun times. Yeah, have fun. Google those equations and let me know. And
Isn't there something to do with?
hey, well, you know what, Austin, once you figure them out without wind resistance and without the wind there, then you can talk to me. Then we'll talk about it in a wind, like a force field of wind and gravity.
I was to say, isn't there something to do with lift with the golf ball too?
Absolutely, yeah. Now, the simplest equations that you can, so the equations that sort of determine the flight path of a trajectory, they're called differential equations. And, you know, we've studied those briefly in calculus too, but they really turns into what's called a system of equations, which is more than one, and they're quite complicated. But yeah, that would actually be a good, we could probably design a pretty cool project. And it would be a little beyond Calc 3, but you could probably get to the bottom of doing simulations and showing that theory and practice match. Because like a golf ball is deterministic. We know if we hit it, it's eventually going to come down, right? Soccer ball, you could kick it. Eventually, it's going to come back down, and we can determine that. It's not like some, you know, microscopic particle, which we can't really figure out how it behaves. And we got a whole new branch of physics for that. It's called quantum, the theory of quantum. Okay, so let's sketch the proof, and this will be scary, but I want to do it because it's one of the first, when I learned this, as I said, 20 years ago. That's right, I was supposed to post my final from 2000, the legend of exam writing, Dr. Labello at Allegheny. Many of the ways I write questions is stolen from his humor and insanity. We'll have to post that for you, and we say if you pass this test, you don't even have to take mine. That'll be the rule. Okay, let's sketch the proof. It's a good little exercise in advanced mathematics. So what we do for simplicity is we're going to assume that this region we're dealing with is very well behaved. So assume C and D look like, we want a special kind of region. So let's get our X and Y axis. Stop. Move. There you go. The word, come on, stop it. My pen. I think this pen's going bad. It's very unfortunate. So we're going to make it look like a real pretty region right away. So let's, oh my God. I'm losing my mind. So let's get like an ellipse or something. I wonder if this will work for us. I wonder if I can sort of make this. I don't want it to be a circle. I want it to be a friggin' ellipse. So how do I get it to shrink? There you go. And then I want to rotate it. Can I rotate? No.
Just shrink the circle the other way to rotate it.
What do you mean, like this? I want it like, I don't know, whatever. I'll just draw a stupid ellipse. This is where my head's at right now. We'll go free form. That way we can have different colors anyhow. So imagine you have some sort of ellipse like this. Well, it doesn't even have to be an ellipse. It can be curved like that. And what we want to do is we want to make sure we can describe, we want to describe this region's boundary as simple as possible. So what I'm going to do is I'm going to put like, you know, a point right here and then say, you know, a point right here, because I want to describe this region as, remember, we're in the XY plane, so we want to describe these curves in a very simple way. So this is going to be our D, and then of course this is C. And we want to think about this region having two curves. So let's imagine that my object is moving around like this. And then we have two pieces. So we're going to call this piece down here, we'll call this whole thing is C, but we're going to break it into two different colors. So let me get another color. And this piece that's down here, which is in green, I'll call this C1. And then the other piece, which I'll put in this light blue, I'll call this piece C2. So we're thinking of, to travel around C, we can think of C as the whole, or we can think of it as the sum of its parts. So how do you write that is remember, C is some curve, so it's a set of points. And so how do we write sets of points as adults? Well, sets of points is, we would write it as C is some curve, it's a set of points, and it's the union. Remember this symbol, this U, it's called union. It's the combination of C1 and C2. And notice that the way I've drawn this, C1 and C2 have very simple, they can be written as functions. Y equals f of x, y equals g of x. Because I didn't write it as just some arbitrary curve. Notice I put those black dots so that I could write these as functions of one variable. Now remember, if I give you any curve, no one said there's a unique parametrization. In fact, could be infinitely many parametrizations. I mean, we made that note even way back when we talked about how do you give the description of a line. There's infinitely many ways of doing it. Okay, now, I want to give names to these things, so we'll get C1. How do I describe C1? Well, it's going to be some function y as a function of x. I don't know what it is, so I have to give it a letter. Now, I already used capital F. I already think of little f and little g as the components of capital F. I usually reserve R for a parametrization, so what's another letter? Let's use G. So we'll call this G sub 1 of x. And then we will use C2, this piece will be given by this equation, y equals G sub 2 of x. Now, suppose in the real world, my region is not as elliptic as this thing, or as nice. Well, that's okay. We can modify the proof, but the proof is easiest done if we assume this simple shape. Now, here's the other beauty of, notice where I put those two lines, or those two dots. These two dots were in a place where, hey, okay, my domain for both functions is, let's say, a to b. So x ranges between a and b. This is fun. Fun, 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 fun. Does anybody have a question? Now, if you're a little overwhelmed by this, that's called your normal. But most of you have had me for multiple semesters now. I think at some point, you've heard me say it over and over again, you can't rely always on just doing examples. That doesn't teach you anything. You don't learn anything. You don't discover. Sometimes you have to suffer through what's happening. And I'm not pretending you're going to make sense of this today or tomorrow. Hell, some of you will do well in this course and still have no clue what Green's theorem is meaning. You'll just know how to do the problems, whether because you looked them up or you did enough examples on your own, right? But this is me pleading that, hopefully you'll try to learn what's happening. Okay, so what we want to do is we want to prove Green's theorem now in this scenario. Okay, so here we go. It also helps just because it's going to be a little more familiar notation. Believe it or not, it also helps to write this integral instead. Let's write it in this notation. F dx plus little g of dy. And what we're going to do is we're going to look at these pieces and put it all together. Now, we don't have to do this. I'm just saying it helps. And why does it help to use this f dx? Because we notice that we're not using a standard parametrization here. We're using old-fashioned y equals g of x for our curve. Okay, so here we go. Fun times. Let me move my can here. So if you go back 2 pages, Green's theorem says what we want to study is we're going to start, it might seem counterintuitive, we're going to start with the right-hand side. We're going to look at this double integral, and we're going to make it look like a line integral. And then that's going to prove the theorem. Okay, so let's start. With the following. So we want to start with this partial f of y dA. Now, we know by Fubini's theorem, we can write this double integral as an iterated integral. Why do we know that? Well, the theorem, we assumed that f sub y, the partials, were continuous, right? We assumed that. So since they're continuous, Fubini says, all right, you can write this as an integrated integral. Okay, so how do I want to do it? Well, let's go back to the picture. Let's look at the picture. The picture says, when I want to do integrated, I have to ask, do I want to do, let's go like this. I'm going to write it as the following. So do I want to do dx dy or do I want to do dy dx? Well, the way I've written my picture in the previous one, the way I've broken my curve up, dy dx seems to make sense. So why do I say that? Well, let's go back, because if we do dy dx, if we integrate y first, that means we're holding x fixed. And so if we hold x fixed, then what we're asking, if we look at this picture, if x is fixed, then we're going between this curve, the green one, up to the blue one. So we'll integrate up first from this curve to the top curve. And then once we do that, then we'll go from A to B. So what does that mean? That means that this integral, we start at the bottom, which is g sub 1 of x. And this is g sub 2 of x. and then this is just a to b. Now, let me be even more clear, if I can. Let me take this eraser. Do not forget for a second that the partial of f with respect to y is a function of x and y. So let's put that explicit. You know, I didn't write it in the other parts because it's understood, but it's going to be helpful if we see that right now. Whew, my head's getting, this is like we're getting naturally high on math. Of course, you guys aren't. You're like, this is crazy. What are you making me learn this for? Austin's thinking, when will I ever use this in my life? Although I saw a good article about that. They're like, the difference between students now and students 30 years ago is that now all students are worried about is grades and jobs. No one wants to learn. You believe that? I said, that's not true. I said, Austin's worried about jobs and grades, but he does want to learn. This is what I said. I thought of you when I read that. Okay. Now, one of the things I mentioned last class was the fundamental theorem of calculus, and I mentioned it at the class before. So last Wednesday and on Monday, we talked about this. The fundamental theorem of calculus gives us a way of writing this integral. So let's sort of give some, I like to give reasons what we're doing here. This is good old Fubini. It makes us sound smart if we tell everybody why that's true. Fubini tells us this is true. Now, what I'm going to write here is probably going to be a big jump for many of us, but here we go. Inside, I have a derivative. And the fundamental theorem of calculus from back in Calc 1, in Calc 1 and Calc 2, we really only thought of it as a way to evaluate integrals, right? Find an antiderivative, plug in the numbers, subtract. Well, guess what? We can do that in theoretical ways too, because this inside integral, the integral with y, being that the partial is with respect to y, we can apply the fundamental theorem of calculus. And so what you get is the following. You get f. Now this is no longer a partial. This is f, and it is x comma g sub 2 of x minus f evaluated at x comma g sub 1 of x. So this is the fundamental theorem of calculus. Whew. Does anybody have a question about this? Notice I took f sub y, so the partial with respect to y. If we just think of that as if we don't notice that in the second line, the x component didn't change because I'm thinking of f as only a function of one variable, just as y right now. And so if I undo the derivative through integration, the fundamental theorem of calculus tells me it's the difference at f evaluated at its boundary points. Okay, now we're going to make another jump. What we want to do now, remember, our ultimate goal is to get line integrals out of it. Oh, by the way, I forgot a parenthesis. There should be a parenthesis right here. Now what I'd like to do is I'd like to write these. There's two integrals here if I want. It is one, but I can break it into two. These are line integrals. They don't look like it, but they are. They're line integrals of scalar functions, both of the function f. So let's think about what this equals. This equals the integral along c sub 2 of f dx minus the integral along c sub 1 of f dx. Now, probably the best way for, by the way, hold on, I have to be very careful. I'm not going along C2, I'm actually going, I'm reversing it. I'm going the other way, so this is minus C2. So let's make a very, this is something I may have not have pointed out earlier. To be completely full closure. If C looks like this, if it's going one direction, call this C1, then the opposite direction, if I go the other way, that would be negative C1. And the reason we say that is just imagine if you switch directions, you're going to get a minus sign out front. Think of it. You know, if you integrate from 0 to 1 and then you integrate from 1 to 0, all it's going to do is it's going to flip the minus sign. So you're going to get a negative sign. So how do we illustrate that if we take a curve and we go one way, then the number we get in the line integral is the opposite as if we go the other way? We just say that C1 is, if we go the other way, it's minus. Again, if I go back to this picture, when I integrate from A to B, it's fine on C1 because I'm moving from left to right. When I go from A to B along green, I'm going in the direction that we originally go. But if I go from A to B on the blue one, I'm going against the natural direction. So that means we're opposite, so it's minus. That's why I wrote minus C2 here. Now, another thing I can ask you to do if you really want to make the connection for these steps is work from the bottom up. If you work from the bottom up, it might be a little easier to see. What's your parametrization of C2? Well, you could write it out as some R, but it's just as easy to say it's dx because you're already written y equals g1 or g2 of dx, or excuse me, of x. Okay, so from that same reasoning that I just mentioned, that if you reverse the direction, you put a minus sign, and that is a more general thing of going back all the way to Calc 1. If you flip your bounds, you negate the integral. Again, we talked about that way back in Calculus 1. So what that means is that you now can apply that fact here. So going along C2 in the opposite direction is the same as putting a minus sign in front of it. So now we have minus and minus, and since an integral is additive, that means if we have the pieces, we can combine them back to 1. What we've just determined is the original integral that we studied, this integral, is actually equal to minus the integral around C of f dx. That's what we just showed. I'm not suggesting it's easy to follow along. I would encourage you to try. And now we can do the same thing on the other piece. I'm not going to go through it, but you could if you wanted to. Similarly, what you can show is you can show the integral of the partial of g sub x dA. You can show that this is this creature. It's almost an identical argument. You just have to write instead of integrating dy dx, you integrate dx dy and do the same thing. And then if you have two pieces to the puzzle, you can put them together, and that's when you celebrate. For the following, what do we can conclude? We can conclude the following. If you add up the pieces, you get that, take the minus sign to the other side or however you want to do it. Doesn't matter how you do it. If you add up the pieces, you get this. You get the partial of g with respect to x minus the partial of f with respect to y dA equals this line integral. That's a bad D. Getting sloppy. Fun times to be alive, my friends. Fun times to be alive. And that's the proof. Isn't this exciting? All right, now. Would I ask you to do this? No. Will I ask you to use it? Yes. Does anybody have a question? A comment? A concern? All right, let's see this thing in action. By the way, if you look at the homework, you'll see the one question I ask you to do, I say, here's a line integral. Do it two ways, by definition and then using Green's theorem. And the reason for that is oftentimes the definition of a line integral, even when we can do it rather quickly, is much more work than applying Green's theorem. Does anybody have a question before we do this? Okay, so let's do it. Example time. And then we'll let you go home and suffer through all the fun. Well, I shouldn't say suffer because it's fun. Who wouldn't want to do all this crap? This is exactly what we live for, I think. What is it? Did you guys hear this upstairs? What is happening? It's funny, like it looks like Dakota, or it looks like Austin's shaking. And all I hear is thumping above me. These kids, you can't trust a 5-year-old. They listen about as well. Well, I don't even know. They don't listen. Okay. What is happening upstairs? Okay, here we go. Anyhow, let's compute this creature where f equals this. Ricky, go upstairs, Ricky. Yeah, that's her book bag. You want to say hi to people? Come here. Come here. Yeah, I know, it's Yaya's. Come on. You don't bite her. That's not nice. All right, go tell her you love her. Go give her a high five. Okay. Stop hitting me. All right, and what is C? C is the rectangle. With the following vertices. So, Ricky, you can't come in here right now, honey. Here, write this down. I gotta go. All right. All right, did I make any mistakes here? I don't think so, no. All right, so here's the problem. Does anybody have a question about the statement of this problem? So let's draw the picture real quick. Just, it's always nice to draw pictures if you can. So if I take these points, I have 0, 0, 4, 0, 4, 2. So here's our rectangle. Let's draw it nice and pretty because we can. So here's the thing that we note, and this is what's most important to sort of get in your head. If I wanted to compute this line integral, it's going to require how many integrals? Well, it's going to require 4, because I would have to parameterize all 4 sides of my rectangle. So let's make sure we understand that. So to compute this directly, requires 4 integrals. Again, you need to understand that. That's the most important thing, because we can't parameterize that perimeter, that rectangle, with just one curve. We would need 4 pieces. We need the bottom, the side, the top, and the other side. Oh, by the way, I should mention this. If you read the top of the homework, you'll notice that I put on the homework, all line integrals, we need to imagine that the orientation is counterclockwise. That's the convention. We talked about that last class. So what I really want you to understand is unless I otherwise state, always imagine that we're moving along the curve in the counterclockwise direction. Does that make sense? That's the convention. Another way to think about it is when you're moving along the boundary of some region, you always think about you need to be moving so that to your left is the interior. That's the way to think about this convention. Okay, so this creature would require 4 integrals. Not that they're necessarily hard, but that's a pain to do 4 integrals. You'd have to parameterize all 4 of those lines. It ain't the end of the world, but it's still a pain. So what we're going to do instead is we're going to use the Green's theorem. So Green's theorem tells us that f dot t ds over this curve is the double integral over the domain of what? Well, let's remind ourselves what everything is. So this double integral is, we take the second component of f, so this is g sub y, excuse me, g sub x, I'm getting. By the way, there's symmetry with this. You know, g is the second component, but we take the partial with respect to the first variable, which is x, and then y is the first, excuse me, f's the first component of capital F, but we take the partial of the second component, which is y. So let's remind ourselves of what everything is. This first thing is Green's theorem. And now this is a very simple integral. We can go 0 to 4 and 0 to 2 because it's a rectangle. It's flat. So it doesn't matter if we do y or x first. Let's do, since I wrote 0, 2, that was my y direction. That's dy dx. Now, what's g sub x? Well, don't forget, what is f? So f was what? Well, the first component was what? 3y. Let's go back. 3y plus 1. And the second component was 4x squared plus 3. So let me remind you, just for the sake of full being complete, this is f, this is g. So if I take the partial of g with respect to x, I get (8x), and then if I take the partial of f with respect to y, I get 3. So that complicated, at least in length, line integral reduces to a very simple double integral. The bounds don't depend on any variables. In fact, only one letter shows up, so that's exciting. When you integrate with respect to y, you get axy minus 3y, and this is evaluated from 0 to 2. So I'm going to set y equal to 2, and you get integral 0 to 4 of 16 minus 6, and then so 16x, excuse me. And then, of course, when I plug in y equals 0, it just goes away. So then now I integrate with respect to x. So I'm left with 8x squared minus 6x from 0 to 4. And let's just save ourselves the headache of doing all this. My kids are so funny right now. Can you hear them right now? You gotta be nice and hug someone. Meanwhile, she was just beating the hell out of her. All right, so if I plug in 4, I get 8 times 16 minus 24. So this, I believe, is 104, unless I made any error. This work from home shit is fun. Actually, it's not. Like if I lived in like an apartment with these 3 knuckleheads upstairs, if I lived at my home with my parents still, like if I were you guys and I was, well, I don't know if maybe some of you don't live at home, but when I was in college, I would have had to go home and live with my mom and dad. I would have like probably rather ran through a wall. I had to go dig a hole in the woods and live out in the woods. All right, does anybody have a question about this? This is fun, isn't it? Does anybody want to have a comment about this? And by the way, you know what? If you want to enjoy the beauty of Green's theorem, you should do it directly. Compute that line integral the old-fashioned way, using 4 different curves, or in that case, they're lines. But okay. Here's a cool fact, which we could ask you to derive. When I was in grad school, on one of our big tests, we had to prove one of these. Let D be any region with boundary C where Green's theorem applies. Then here's the fun part. Then the area of D can be computed in one of 3 ways. You can compute it with this line integral. You can compute it with this line integral. And it's also equal to this line integral. So this is a pretty cool thing. It basically says that the area of an object is somehow dependent on its boundary, which I guess makes sense intuitively, right? You would imagine the longer your boundary is, or the longer your perimeter, or some properties of your perimeter would have something to do with your size. Now, this actually is very important in the real world in the sense that it's the basis behind a very important tool, what you can Google and read all about if you'd like. So you can Google, and maybe you know what this is. It's called a planimeter. So what it is it's a tool that measures. So if we have an arbitrary shape, this tool, Google it, you could see how it works. It gives you the area of an arbitrary shape by tracing its perimeter. And the reason it works is based off of Green's theorem. It's pretty fascinating. Check it out. Google it and read all about it. So let's do one more example real quick. So let's consider consider a circle of radius, we'll use big R, centered at the origin. Well, how do we define C? C would be this parametrization. It is R cos T comma R sine T. That's the parametrization. Let's not forget these guys. This is our X. This is our Y. That's how we parametrize a circle. We learned that a long time ago. Okay, so let's compute. What's the area? Let's use the first one. So the area equals this line integral of, let's use this, the x dy. Well, what is this line integral? Well, we know what x is. This becomes the integral from 0 to 2 pi, because that's where theta or t range is. What's x? X was r cos t. What's dy? Well, that would be the derivative of the y component, so that would be r cos t dt. So again, these are jumps that we have to, this is x, and then this guy is dy. Okay, great. So what does this integral become? You could pull the r's out. This is r squared. Oh, how the hell does that happen? And then the integral from 0 to 2 pi of cos squared t dt, which is an integral from way back in Calc 2. One way to do it is to write this as 1/2 times 1 plus cos of 2t dt. Which is 1/2 r squared. And now I'm going, well, let's just write it out slowly for the peeps at home. 1 plus cos 2t dt. So it's 1/2 r squared. Now this is an integral from back in the day. You get t plus 1/2 sine 2t evaluated from 0 to 2 pi. Plug in 2 pi, you get 2 pi plus 0 minus 0 minus 0. And of course, as you expect, the area is pi times the radius squared. Now, you might say that's a lot of work to prove a simple fact, but I don't think you guys remember proving the area of a circle is pi r squared is not a simple fact. It actually requires integration no matter how you slice it up. Whether you do it like this or whether you use some of those crazy trig integrals we studied back in Calc 2. Calculating the area of a circle is in proving this result that we tell kids to memorize in 7th and 8th grade is not an elementary fact. It's quite complicated. Intuitively, it makes sense, but to actually derive it, it's complicated. So there you go. Does anybody have any questions about this? All right, well, listen, I'm going to wrap it up then. You guys work on those problems. If you have questions, please let me know. Let's plan on meeting Friday unless something happens here where I can't. And then don't forget, next week I'm going to give you your quote-unquote final and maybe some extra credit stuff, whatever, and then you guys can work on it as much as you want. All right, any questions? All right, guys, well, I'm going to stop recording, and I will post all this to the internet and everything. All right, have a great couple days. Be safe.